Welcome back to the molpigs podcast. Today our guest is Jacob Majikes. Also here today are Boya.
Hello.
Eric.
Hello.
Georgios.
Hello.
And I'm Hannah. Jacob Majikes is a research scientist in the Microsystems and Nanotechnology division of NIST. He received his BS and Ph.D. in material science and engineering from North Carolina State University. His doctoral research focused on probing the folding and assembly of DNA origami nanostructures. Jacob is also an executive editor of the Art of Molecular Programming textbook, which we've talked about before on this podcast. And this year he took up the role of co-chair of FNANO. Jacob, hi.
Hi, how's it going?
It's going well. Thanks for coming on. So we always really start with the same question. So this podcast is going to be no different. How did you get into molecular programming?
Okay, so mostly by chaotic happenstance. So from your bio, you introduced me as going to the same university for graduate and undergraduate. What I didn't mention online is that I was also the second graduating class out of the middle school on the NC State's engineering campus. And so by the time I finished my undergrad, I was quite ready to leave, and I was planning to leave. But I started dating this girl that I had known since we were in elementary school together. And I had wanted to date her for ages. And she ended up going to get her graduate degree across the street at UNC, which is, 40-minute drive. And so I kind of shopped around for a good excuse for why would I stay at the same institution for graduate school and undergraduate. And it turned out Tom Levine, who was my PhD advisor, was just moving to Duke. And so I knew all of the safety stuff. I knew the facilities information. And so I figured, well, I could, basically start off transitioning his lab and helping out with lab management. And that would be a great excuse on my resume for why I stayed in the same place. But really, I did it because I was, dating this girl. It appealed to me because I had done polymer work before that, polymer self-assembly. I had started off doing experimental work, and then I transitioned into theoretical MD and coarse grain simulations. And so I thought it was really cool that you could get essentially controlled, programmable phase segregation with, sub-nanometer precision about what goes where. And so the stars kind of aligned for me to continue and then go from polymers into molecular programming.
I think that might be one of the most unconventional routes into molecular programming we've had before.
Yeah, it's funny. The professors in my department were joking that I'd been there longer than them when I finally graduated and got out of there.
So then how did you decide to join NIST?
Yeah, that was also kind of an interesting story. So I realized I wanted to be a professor probably my second year of undergraduate. So I spent most of my undergraduate thinking about what skills I would need to build up. And so I did this also through graduate school. So I worked a lot on management skills and on writing skills. Particularly, I forced Tom to let me help write a grant that didn't go too hot, but it was part of the learning experience. And what I realized when I finished graduate school was while I had built up the skills to do this job that I want, I had not actually built up the publication portfolio that I needed. And I wasn't going to be able to get a position out of grad school. And my network wasn't that great. And so I basically said, okay, Tom has some funding for, I think, half of a year of a postdoc for me. So I emailed every lab that I knew working in DNA within driving distance. So, some folks at Cornell, I emailed Penn State. There were some folks at SUNY Binghamton, at SUNY Albany. They have an RNA institute up there that's quite cool. Johns Hopkins, NIST, everybody. And I basically said, I will pay to drive there. I'm happy to give a talk about my thesis work, and not even asking about a job, just to expand my network. And in so doing, one of the things I asked is, hey, can I talk to you about, some of my long-term research ideas, see if you think they're good ideas, bad ideas. And so I think I ended up giving talks at SUNY Binghamton, SUNY Albany, Johns Hopkins, and then NIST and MIT. And NIST was definitely the best fit. That was fairly obvious, just in terms of the sort of work I wanted to do and the sort of work that NIST wanted to do. For those of you who are unfamiliar, NIST is the National Institute of Standards and Technology, We're a research lab under the Department of Commerce. And so that means we have different incentives and different kind of the way they judge us for quality. And so the hiring process is also a little different. So they do hire like associates that are postdocs that are paid and managed through other universities. But the primary hiring process is this thing called the National Research Council Postdoctoral Fellowship. And this program hires for NIST. It also hires for a number of national labs, as well as the Naval Research Lab and the Army Research Lab, etc. And it basically boils down to a grant proposal. So it's like a 2-page grant proposal, personal statement, that kind of stuff. And the idea is it's a little strange in that you're encouraged to talk to the places you're applying to in advance and to make sure that the proposal is in line with what they're doing, but they're not the ones judging it. So it's being judged by the National Research Council's group of folks. And if you score 97th percentile or above, the funding doesn't come from NIST or from NRL or whoever it was you applied to. The funding comes from a pot of money the federal government gives to the National Research Council. If you score anything above, I think it's like 80% or something, then, and it's different by institution, then the institution basically has the option to hire you on from their own funding. And so I think I applied 2 years to NIST's NRC program in 2 different slots. And the one I applied to second was with the group I had given a seminar to, which was Alex Liddle's group. And then I started on after that.
So when you say that out of all of these options, NIST seemed like the best fit, does this mean that your research directions were already kind of aligned with NIST's mission of kind of measurement and that sort of thing?
Yeah, and I'm probably going to say this in the worst way possible, but I'm incredibly stubborn and I really hate it when we don't understand boring basic details. And there is no better place in the world to do boring, well thought out work than NIST. That sounds bad, but like you got to understand, metrology is inherently, your understanding of your measurement needs to be an order of magnitude better than the level of understanding you want to use your measurement tool for. And so, on top of that, NIST is very interested in the transition from academic research to the real economy and trying to push research in directions that make it more likely to be implemented. And all the stuff I've been working on has been very much the boring materials physics of how DNA origami come together. And that's not the kind of thing that gets you a Nature paper, but it is absolutely the kind of thing that you need to know if, say, you're going to make a company making more than one kind of origami. And so that was very much in line with NIST's mission.
And do you think this kind of boring measurement focus is something that it's good that NIST does it, and it's good that somebody does it, or is this something that you think should be applied more widely across DNA origami research groups? And you'd like to see more of this, basic quote unquote boring research going on among all the labs in the field?
I've got to phrase this correctly, or as politely as possible. I think for any community, you do need a bell curve of what's being done. You need a wide variety of work. You can't have everyone doing the same thing. And I think there's a temptation to say, oh, everyone should do what I do because I'm the best at what I do, and you get social status if you're the best of everyone doing the things. But at the same time, the bell curve of the things people work on is very heavily influenced by what incentives they're given. And to be perfectly honest, I think the incentives in the vast majority of academic research are absolutely terrible. I think that the incentives have driven us as a community away from doing the work that makes science the most valuable to the economy. I think we're effectively, the dream of science is that you've got a bicycle wheel and you're pedaling it, and a chain takes the gear and pushes it to a meter that says, this far until we reach Star Trek. And that chain has fallen off decades ago. And so, it sure is easy to pedal your wheels. It's not necessarily easy to do something that matters. And I think a great way to emphasize this is every professor I know in research, not just in DNA nano, just in basic research at university, has a small business that is spun out of their lab. It is virtually always being run by a student or postdoc who has difficulty getting a job somewhere else, and it almost never gets bought out or commercialized in any meaningful way, which is a really harsh thing to say, but I think it's a true trend. And I think the reason is because university research is heavily incentivized both by not having a lot of time and by the NSF and the various funding agencies really caring about things like nature papers and novelty, which means that we end up doing a lot of qualitative work that we don't end up validating very well, and that you can make the coolest thing in the world, and if nobody else uses it, it was just, a fun little macrame project. Um, so yes, I think more people should be doing the slow, boring research, but I think not everyone. I don't think every institute should be like NIST. But I do think more institutes should be a little bit more like NIST at least.
So why exactly does NIST do this kind of research? Like, how do you go from standards, weights, and measures some number of years ago to DNA origami?
Oh, oh yeah. Okay, so and this is going to be me. Got a very. Oh right, I'm not a federal employee anymore, so that makes this easier. So there are actually laws that say federal employees aren't allowed to go out in public and explain how the federal government works. In part because I think it's part of the Hatch Act actually. But the
Sorry, what?
Yeah, no, there's actually a good reason for this. Because you as an employee aren't Congress. You're not the one writing the laws to say how and why. And so you actually don't know how and why. You mostly just know the nuts and bolts. And there is a concern that if federal employees go out and explain the nuts and bolts and try to explain the why a little too much, it puts them in a position where they give an economic advantage to whoever they explain it to. So this doesn't matter for this podcast, and I'm not a federal employee anymore. But if this was like for industry, you could potentially give one company a competitive advantage. So this is more like the patent office cares about this. USPTO really cares about this. The way I would frame it, so you need weights and measures. You cannot sell something if you cannot measure it. And you need everybody in a product community to be using the same measurements in order for customers to make informed decisions. In general, everyone is better off when they're using the same measurements and those measurements make sense for the product application. But one of the things that you need isn't just to make standards, right? You need to make forms of measurement. So for example, when NIST does training, the example they give you is guinea pig bedding. Guinea pig bedding, if you've ever had a guinea pig, it's like hay, but they give it to you in this compressed brick. And there's this question of, if you measure the guinea pig bedding by weight, somebody could give you hay that's full of rocks, and they could say it's cheaper by mass. If you measure it by volume, someone could give you a brick that is not compressed, and they could say, see, this volume, I am giving it to you for half the price, even though you only get, 1/10 the bedding. So NIST works with all of the companies that make guinea pig bedding and horse bedding, and there's actually a standard method by which you measure how much volume of bedding that you're selling. And people, NIST has no regulatory authority. NIST can't force you to use this measurement, but NIST works with all the companies because everyone agrees they're better off if they're using the same measurement. And so there's actually, this happens with NIST a lot of committees that meet with representatives from industry to come up with these best approaches. And that tends to be a lot of what NIST does in terms of person power and effect on the economy. In order to do that, you need people who do measurements day in and day out, right? And, the federal government takes a while to hire a new federal employee. And so you have this conundrum of, you do not know what the next big problem in the economy will be. You don't know when the guinea pig bedding crisis will hit. But when the guinea pig bedding crisis hits, you need not just someone doing measurement, but you need to understand that measurement in order of magnitude better than the customer needs the results of the measurement, which means you've probably got this is me pulling numbers out of the air, 14-year lead time on this new problem. So this happened recently with biologics and biosimilars. So these are protein medicines. And one of the problems was normal patents, you patent the chemical structure and you're done. And that's what the patents for biologics have. But it turns out the way you manufacture it can radically change whether it causes an immune response, can change whether it actually works for you. And the Department of Commerce is sitting there going, we want generic, biosimilar drugs, but we need measurements to be able to confirm that they're good. And we need to work all that through. And that's like a 14-year lead problem. And so NIST basically has a non-trivial, I would say almost a larger than half portion, although, I don't know the numbers, I don't know the staffing, but a significant portion of the folks working at NIST are just doing basic research with the understanding that it has to be focused on measurement, with the understanding that NIST is hiring them to have as wide a variety of expertise as possible and focusing on hiring in directions where NIST thinks the US economy will go. So that the second, let's say Paul Rodman's new company that just got bought out to do single molecule nanocavity origami placement stuff. If that becomes a big thing and suddenly instead of just one company, you have a whole industry and they have some measurement problem, NIST already wants to have all the experts to fix the metrology problem working on board. So that was a very long, convoluted answer, but it basically boils down to this stuff is a lot harder than you realize before you start doing it. And the way I would frame it, and I think this is true of NIST and of universities, is to think of research as the equivalent of retirement planning for the human species. You want to have a portfolio of research happening, and different institutions are like different retirement funds. NIST is unique in that we are focused on the US economy in a very particular way, but you're still making that portfolio of how many risky investments do I have? Do I have all the risky investments in nanotech? Do I have them in bio nanotech? Or do I have a little risky in civil engineering, a little risky here, a little risky there? So it makes NIST a really weird place to work, but a really fun place to work because it means that there's a wide variety of people who all think their technology will be the one with the next big measurement problem, but who also have a really great deal of incentive to do high quality work and to collaborate across disciplinary lines.
I have probably a really stupid question about NIST. Are you guys measuring things mostly in metric units, or is this in like pico-pound nanofeet that you guys measure being part of the US government?
No. We are not allowed to use non-metric units. So in fact, the speed limit on NIST campus is in kilometers per hour. Because the
That
US
is beautiful.
because the government requires it also is in miles per hour. It's in miles per hour below it in a smaller number. So for example, when I write papers, I should say, so one of the things NIST does that I think is good, but also people don't appreciate the amount of additional effort it involves, is we actually go through peer review twice. We cannot submit to a journal until we have gone through peer review at NIST. One of the things that happens in that peer review is they remove any unit that isn't SI. That sounds good, but nanomolar is not an SI unit. It's moles per liter. So every one of my papers is moles per liter. Bases of DNA, that's not an SI unit.
What do you use instead?
Exactly. No, I get in arguments with people over this. My argument is that even though we treat it as a measurement of length, it is not a measurement in and of itself. It is a description of the molecule. And so I use nucleotides and then abbreviated NT, but then NIST gets very concerned if I were to mix and match that within SI units. So I have to take care not to do like nucleotides in a sample, right? So it's not nucleotides per liter, it's just nucleotides on the strand.
So going back to NIST kind of portfolio of technologies, I mean, NIST is a federal institution, but it must have kind of a finite set of resources. How does it decide which technologies are the next big thing, and how did origami get into that portfolio?
Yeah, so this is getting into the space where no one would care, but a federal employee probably shouldn't answer that kind of question. But not a Fed anymore. I'm now an associate. Yeah, so the definition of politics is how humans decide to distribute scarce resources. So the short answer is politics. The long answer is sometime in the thousands, Congress. So what happens with NIST is all of our funding comes through Congress. So on some level, this is determined by Congress, but it's also done in anticipation of Congress. So for example, the physicists at NIST really care about quantum computing. So they will start making quantum computing stuff and focus their work in that direction in anticipation of Congress saying, this is important, here's some funding for it. So NIST made a nanofab because Congress told them you need a nanofab division some years ago. And then the folks who were involved in that, I think the nanofab was done being built, or I think was it around the time origami came out, something like that? And so they saw the origami stuff and they said, oh, this is cutting edge nanofab. This is within our mandate of what we're supposed to be doing research on. This is also the kind of thing where you have weird measurement problems associated with self-assembly and with, how do you quantify yield of these things? And so they, on the discretion of like individual group leaders, one of them brought in the origami stuff. And then over time, that has slowly grown as more people have gone, hey, this might be useful for X or Y. We'll bring in another postdoc.
So moving over to your work on origami, can you give us a little like 2-minute spiel of what it is that you're measuring when it comes to folding origamis?
Yeah, so basically what I'm interested in is, whether or not origami itself ends up being industrially relevant. I'm actually of the belief that origami is going to be like the breadboards you buy at Radio Shack, where you use it to prototype things, but no company would produce a phone using the breadboard you bought from Radio Shack. That's my opinion of what will happen with origami. But using origami as an example of self-assembling nanofabrication techniques, you have this weird problem of an origami consists of, let's say, 215 molecules, one of them many times larger than the others. Of those 200 molecules, they're all multivalent. So you have probably on the order of 600 independent chemical reactions that are capable of happening. And all of this forms a like 5 megadalton, which is a huge molecule, right? And so a lot of your analytical chemistry breaks down. You can't, how do you measure, is this a 5 megadalton structure, or is this a 4.999 megadalton structure that's missing one staple? Or is it a 5.0001 megadalton structure that has 2 copies of staple 35? And there's kind of the philosophical question of measurement, which is, I think, honestly, kind of like what you're doing when you're doing research, which is how do you define the system? What is the yield of origami? Is it total number of staples correctly bound over the total number of possible binding reactions? In which case you could have really high yield, but an entire pool of system of origami of which none is correctly formed. Or is it the number of origami that are 100% correctly formed, in which case you could have a tube with no yield that's incorrect. And you basically run into this problem for our field, I think, where the systems are too big to easily simulate. They're too energetically complicated to use analytical predictions rather than simulations. They're too physically big to do good purification and to do good analytical chemistry. And they're too vaguely defined to come up with an easy definition. And that forms kind of a feedback loop of doom in which we never really know what's going on. And so I basically, when I went to NIST to give my talk, before I ever got a job there, I basically said, the dream is to do this experiment where you design the same origami as many different ways as you can, and then measure the yield and start picking apart what is good design, start picking apart, what are the energetics of individual folds, how do those sum up? And NIST was like, oh, that's great, figure it out. And so I spent the first 3 years I was working at NIST just trying to measure individual folds. What are the loop entry penalties so that we're not extrapolating from biological fits to models? Because like the biological model that is used, I think it was fit in the 80s, and the functional form was derived by de Gennes, who's one of the fathers of polymer chemistry, for the vulcanization of rubber. Because when you vulcanize rubber, you're forming rings of polymer. And anytime you take someone else's research and apply it out of context, it becomes chaotic. So I spent the first 3 years trying to do measurements of individual folds, trying to get a sense of how these things add up with each other. That project never fully took off the ground. And trying to get a better sense for how good does the measurement need to be to get the error bars as small as we need them, to fit the theoretical equations to the level we need them to be fit to. And then how does all of this propagate? So, that's where it started. And then recently things have gone far enough that I've done that experiment of designing the origami a million different ways and try to look at trends in yield. And so what we're really trying to do is work from for lack of a better word, from the top down and the bottom up simultaneously and try to get them to meet. And that has been not as successful as I would have liked because it turns out the problem is unexpectedly rich.
So with the richness of this problem, do you ever find that there's any research you want to do which maybe doesn't fit the measurement criterion or is difficult to kind of argue is within the scope of NIST, or has everything you've wanted to do fallen into this category?
Most of it has, but that's because, as researchers, you can't be a researcher without being good at reframing the work you want to do within the framework that someone else has made. So, there are a few things that are a little further out, but you can't do science and engineering at the nanoscale without doing measurements. So in a lot of ways, I could have gone those directions and NIST probably would have been fine with it. I might have had to work a little harder to convince my boss. But no, that's not so much been a problem for me. But I also am a little bit interested in everything. And so it's easy enough to say, okay, I'm going to tailor what I am doing around what the people who are giving me money to do it would like.
So you're saying that you think DNA origami's place will be more as like a breadboard for positioning. And obviously DNA origami has had a massive impact on positioning of nanoscale structures, but it's also done kind of non-positioning things such as Carlos Castro's work on functional origami and the ideas of drug delivery cages. Where do you see the landscape of origami?
Yeah. So I think what I would say is, what is it? When you can't say something insightful yourself, you quote someone else. And the quote that always comes to mind that I don't remember who said it is, engineering isn't complete when there's nothing left to add. Engineering is complete when there's nothing left to take away. And the fundamental question you have for any possible killer app for molecular programming is, what is the smallest possible nano thing that I could make that would achieve this application? And so there are some nano things where the size of origami is such that you wouldn't want to take much away from. So one of the projects I'm working on at NIST is building a signal amplifier for impedance measurements on an electrode. And we actually think we'll be able to get down to single molecule kinetics binding measurements. And we have a pathway to doing kind of the dream of multiplexing, which is to cross-correlate measurements from, hundreds of electrodes, which you can then do basically to do the olfactory thing where you have lots of weak sensors instead of one very strong sensor. So that's one where you could use DNA origami. But in most cases, I would argue almost all of them, you could not have 95% of the origami by mass, and it would still do its job. And if that's the case, why would you pay for that 95% extra mass? And that's where I feel like with the breadboard. To be honest, I would guess that people will probably use smaller plasmids, and there will just be origami that are mini. But that's all kind of reading the tea leaves.
So are there any do's or don'ts of origami design that you've learned from your research that you want people to keep in mind when they're doing designs in the future that you think you've solved and we don't need to worry about this potential pitfall anymore?
Yeah. So I thought I was going to have a bunch of them, and I thought they were going to be super insightful that no one's ever done before. And this project has defied my expectations and gone against every hypothesis that I put up there, which is deeply depressing and also really interesting. So I would say one thing that I would caution any engineer of is the human brain has a really deep-seated desire for symmetry. There's a strong human bias for symmetry. And often we will see something symmetric and go, that is right, even when it is not. So anytime someone says they know how to design something and everything they design is symmetric, and there isn't a physical reason why it's symmetric, that usually means they don't actually understand the system as well as they think they do. So that was one of the things I set out to test was, if you move the seam, right, you make the seam asymmetric of an origami. Presumably that will reduce yield because you're increasing long loop distances and decreasing mid-length loop distances. But if you interdigitate it, in theory, you should have a smoother funnel of the free energy unfolding. So I thought that would actually improve yield. Didn't. Dramatically reduced yield. So I have no idea, and it appears to be the case as well, that like the more symmetric staple patterns seem to work more. No idea why. I can come up with some kind of pulled out of the air reasons, but it seems like the human bias for symmetry mostly works well enough. So I would say until we know better, keep following the human bias for symmetry. We were able to confirm that pulling the sequence of the scaffold through the structure didn't seem to make a big difference. The steric hindrance of the excess single-strand DNA can definitely make a difference, which I don't think anyone's surprised by. The length of the staples and the distribution of domains on them appears to make a difference in yield, but not in a way that we can predict. So what all of this boils down to is follow the biases you already had. Instead of spending person hours optimizing the design, don't do that because you actually can't predict whether the design will be good or bad at this point. Instead, spend that money on prototyping it quickly. Order a small scale synthesis in like the pre-pooled ones that are sold that are cheaper, right? And iterate quickly rather than trying to optimize something when you don't have a true heuristic on which you can optimize it.
So were those findings of yours simulated? For example, like have you ever tried to match your design to like Ox-DNA prediction? And do they match? Do they align with each other or not?
So predicting yield is pretty difficult So in fact, that was one of the invited talks at FNANO this year was folks, I think they used a variant of OxDNA to do some kind of yield prediction, and this was out of, oh, I can't remember, one of the professors at Duke.
So it's actually it's an even coarser model than OxDNA, and I believe they have some back propagation to OxDNA to do final refinement, but it's a totally new model,
Yeah.
and it's able to actually fold things, which is beyond the scope of OxDNA.
Yeah, and I actually spoke to them after FNANO, and the system I am working with is bigger than they would have simulated before. They think it's possible to be done, but they also had only simulated things at a 1x staple excess, and they hadn't included improperly synthesized staples, which are a sizable portion. And so I would love it if we could get those simulations. I think they might yet be coming in the future, but we do not have them right now because they're pretty difficult.
People build origamis kind of without purifying staples, and kind of this has been pretty successful since the beginning. I think originally it wasn't, or at least Paul speculated on why this worked well, but have we developed any better theoretical understanding of this since then, and how to improve yields of what were already pretty high, if I remember right?
Okay, so now I'm going to be the pedantic NIST guy. Define well, define how you mean when you say that you have high yield. And I think part of the problem is when we as a community say we get high yield, what we mean is most of them look pretty. And especially when you have grad students who are going out and measuring the thing and then giving their best images to their PI. And then of those images, the PI picks the best images to put in the paper. Not to say that the yield isn't good, just to say that I don't think we actually have a definition of yield. But I think there is a consensus. There are not that many people working aggressively in this space. You've got some folks jumping in and out. You've got, I think, Aldrich has been working pretty consistently in this area. Barbara Saka, I think, has been in this space, but with the mechanophores, where you have the crossover can be at two different angles. But it seems as though the consensus is that because you have these multivalent binding positions, and because DNA can do strand displacement, anything that's poorly synthesized by definition will have a weaker binding than the thing that is well synthesized. And the probability of reaching a state that is truly kinetically trapped is actually low given the number of binding domains on each staple. And I would guess that's part of why the staple motif can have a strong impact on yield, but we have a hard time predicting it because there's some optimization of the probability of being in a kinetically trapped state of binding a poorly synthesized staple as a function of the length of the domains and the number of domains and how those domains are distributed with loop entropy penalties. And I think that's going to be a really kind of gnarly problem to solve.
Do you think it is possible to solve that? Can we get to 100% yield by the kind of most purest definition of 100% of the structures have 100% of the staples in the right place? Or is that just not statistically or thermodynamically possible? At least for 2D origami, and I don't know if it is even conceivable for 3D.
I think what I would say is I think you actually asked two questions. The first question is, can it be solved and optimized? And I think the answer is definitely yes. Can it ever be 100% yield? Absolutely not. I mean, by definition. So, there's actually, this is one of the slides I use in my talk, but, Moore's law, right? He actually has an excellent quote in it where he says, the reason that we can do semiconductor fab to these levels of precision is that we are so far from equilibrium. By definition, self-assembly has to happen at least within the ballpark of equilibrium because you need to be able to explore different conformational states and different binding states. If you can explore different states, you have enough states within the thermal variation of energy that you will always have an equilibrium population of defects. And that's great. That's what lets us have self-assembly in the first place. But it also means that you're going to have an equilibrium population of defects. That's unavoidable. Now, the next question, though, is how do you define yield? Because if your yield is defined such that you only care about defects that matter, which now you've got another poorly defined term, but then you could say, yeah, I don't care about any defect that doesn't matter. Well, now you might be able to get up to those high yields, but now you have an even more complicated philosophical problem to solve, which is what does matter mean? So yes and maybe.
if we compare DNA origami to the guinea pig bedding problem, what measurements do we have now to kind of uniformly characterize DNA origami for kind of commercial applications?
So so the focus of my work has not been making new measurements. The focus of my work has been taking traditional measurement techniques and figuring out how to use them more reliably. So for example, I've spent a lot of time figuring out the uncertainty statistics associated with counting images, which, I mean, that's not necessarily that new. People do it in cell counting all the time. It's just this is a slightly different problem from cell counting. Other systems I've worked with is how do you use something like a real-time PCR as a temperature-controlled florimeter? Because part of the problem with origami is you need to measure way more things than you can measure in a traditional florimeter that only has 6 to 12 cuvettes that can fit in. But if you go to something like a real-time PCR unit, you now have all sorts of optics alignments in each different well that can influence your signal. And so how do you get a consistent result when you move into this measurement space that is still well understood, is still common, but wasn't necessarily designed to address origami problems? I think we're still far away from new measurement techniques that will be really tailored for origami, in part because this whole 5 megadaltons being at a space that's difficult for analytical chemistry thing, that's a really hard problem. And it's not one we put a lot of effort into as yet as a field.
This year, you were co-chair of FNANO. How did this happen? What's the story behind that?
Yeah, basically, John at Duke has been organizing FNANO for the last 20 years. And that's a tiring task. There aren't a lot of fields where you have one group of people organizing for a long period of time, at least not to that level. And they basically ran into an issue where John has been open about it, but I'm going to, minimize details. The health-related stuff that thankfully has been mostly resolved. But like with COVID, post-COVID, it's one of those no one's taking their health for granted. Will I be in a position where I can go to this conference next year? And no one wants to put in all the effort to organize a conference if they're not going to be able to go. And so when the committee that runs FNANO was having these discussions a little more than a year ago, they realized that they wanted to bring in more person hours from outside so that there wouldn't be as much of a burden on John and Andrew. So John does the logistics essentially, and then Andrew helps organize the track chairs for the technical program. And even though FNANO is a comparatively small conference, it's still logistically challenging to do. And it's logistically challenging to have that organization fall on so few hands. And my PhD advisor was in that room in that conversation. And I think basically they looked at each other and said, who do we know that's a sucker? And then Tom was like, oh, that Jacob guy. And that's basically what happened. And then there's been a bit of figuring out of what things should I do, what things am I not doing, and also, how much longer does John want to keep doing as much as he's doing? How much longer does Andrew want to keep doing what he's doing? If they're not going to keep doing it, how much is Jacob physically capable of taking on? And all of those questions are up in the air. So a lot of our discussions have involved the three of us looking at each other going, and then like 15 layered if statements, of, well, if future folds out this way, here's what we'll do. And hopefully it'll be easier for us to predict what'll happen if I get a tenure track job and, as, general life chaos and post-COVID chaos starts to calm down. It's also interesting because FNANO was very much optimized to be a get new people into the field conference. So, one of the things I brought is I made a Google form so that we can look at the demographics and ask some basic questions. And I think was it 60 or 70% of people at FNANO had never been to an FNANO before? It's a pretty large number. And so you have this interesting issue of we still want to have this function of this conference, bringing new people in, bringing new ideas in. But what does that look like in a field that's maturing? And I actually have very different answers, I think, than John and Andrew. And that's been one of the things we've been discussing is, okay, what does this look like? What does a responsible path look like? Because you can't just go in and change things. There's a reason it's been done this way. But you also can't run it infinitely the same way. And I think what's going to be interesting is maybe in some countable number of years, as the field continues to grow, FNANO and DNAX will probably not be sufficient just because the sheer number of people who have work to present, right? And we're going to have some weird and awkward conversations as a field about, do we all just go to American Chemical Society or to some, European conference, or do we spin out a third conference? If regardless of which of those things happens, does DNAX just get really big? How does that change the original conferences in the field? Because DNAX and FNANO have been organized the way they've been organized for quite some time. And those are always incredibly difficult cat herding questions, and there's no right answer. And I think the most we can hope to do as a community is to be very patient, make steps when there is consensus around them, occasionally make steps when there isn't consensus, but be aware that there are a lot of people in our ecosystem who rely on these conferences, and there's probably not a right answer. In fact, I would say there definitely isn't, because you can look at the feedback for these conferences and for anything, and you'll hear the people who say this is a problem, it must be this other way, are usually equal in number to the people who say this is the best aspect of this and everyone loves this aspect. And so there really is no winning. And I think the best we can hope for is to be as thoughtful and considerate with it as we can. Lord knows what that looks like.
Is there anybody else that you're looking to bring in kind of in your generation of the molecular programming field as John and Andrew kind of step away from FNANO organization to be that second co-chair or third, fourth co-chair of this conference that seems to have the same chairs every time as opposed to DNA?
Yeah, no, this is actually a really interesting question. It's one, I think I've only talked about this for about 5 minutes with Andrew and John. So this is really out there. So, we don't necessarily know if I can't get a tenure track job. This is a whole different question because I probably am not going to go to industry and keep organizing FNANO. And right now, FNANO is really optimized for what it's good at, which is bringing in new ideas, going to people out in the world who are doing molecular programming, who don't think of it as molecular programming, and saying, hey, you're a molecular programmer, and to prove it, we'll give you, a free registration, come give a talk. And that has a lot of really positive benefits. And one of the things that's interesting is, we clearly need to be bringing in fresh effort, in part because any society needs to do that. But figuring out how much is a really complicated thing, because one of the other questions is, and I don't actually know this yet, I think as of right now, all of the track chairs are pretty happy doing all the work they've volunteered to do. But it's volunteer work. You can't assume that volunteers are just going to be happy bleeding in, tons of time. And so I think what's going to happen most likely is that we are going to rely on the people who have been willing to volunteer for as long as they're willing to volunteer. And then as they, say, oh, maybe I might not be able to do as much, the big thing is going to be we probably don't have more bandwidth. It's not like Andrew can do extra work, or I can do a little extra work, but it's not like John is going to take on extra tasks. So I think it's going to be primarily determined by, when people feel like it's too much volunteering to shoulder, then we're going to panic and we're going to go, oh God, who can do this? And then we'll go to ISNTS, and then we'll go to MPS, and we'll say, okay, guys, who's a sucker? Who do we know that will volunteer to do work for free? And I don't know what that's going to look like yet, because to be perfectly honest, it sounds like John and Andrew are pretty happy with having spread some of the logistics out, because most of what I've been doing has been on-site logistics and cat herding. And so I don't know, and I don't know how much time our track chairs have, in part because I've looked at it, but I've not truly looked at in depth. how much time people have for these tasks as their careers progress. And I know it's extremely variable person to person, but this feels like the sort of thing there's got to be like an actuarial table of, which is a really depressing way to phrase it, but you know what I mean, right?
It's a very NIST way to phrase it.
Yeah, so for the audience, actuarial tables are things that insurance companies use to predict when you will get sick or when you will pass away, so they can tell how much to charge you for insurance. And there's got to be an academic version of this, right? Like something where we're like, oh yeah, the probability that Bob's gonna, you know, change fields entirely and become a quantum chemist is 0.1%, so we should bring on 0.1% of extra person hours from someone else. Someone probably has done that research, but not me.
How likely do you think FNANO will move out from Snowbird?
That is not one that I can truly speculate on. So this is one of the things that I have done a little bit of is to compare Snowbird to what it would cost to do something similar elsewhere. And one of the problems is that the catering industry and the convention industry is a pretty complicated one. So one of the things I will say is that FNANO, part of what makes it work is that it's in the same location every year. If FNANO were to move, which I am not sure it will, and in fact I would guess that it won't, it would need to be in the same place regularly, in part because you cannot have so many new people at a conference and change its location. That's too much. And Snowbird has been, it's hard to articulate this because it's like the real figure of merit is value to the attendee, right? So it's not just the cost of registration. It's the cost of registration as weighted against the cost of the hotel, right? As weighted against the cost of food, as weighted against how much food you get. And so, one of the perennial things that people complain about with FNANO is that we tend not to have as much food, in part because we're charged quite a bit for our food. But also, the hotel rate we get from FNANO is easily 50% or less of what we would get anywhere else. And even if we were to move somewhere with cheaper food prices, we would end up doubling our attendees' hotel costs. So I cannot say anything because I do not know. I haven't finished the analysis. But from the analysis that I have done, it seems like Snowbird is giving FNANO a sufficiently good deal that it would be difficult for us to find a better one. If we find a better one, that it's not just then that we go to it, right? That is then a discussion that would probably have to go to Essence. That's the kind of discussion that I would probably want not just a vote of the track chairs. Although if the track chairs all say we don't want to do it if it's somewhere else, then that's a veto right there. So I think the way I would frame it is moving FNANO would be such a huge task that the way you'll know if FNANO will move is if you start seeing the boulder being slowly pushed up the hill. But yeah, I would say it probably will not move if my current understanding of the deal we get from Snowbird is true. If my understanding of potential deals from other places is as true as I believe that it is. And then on top of that, even if it were to move, that would have to be a community decision. And it would have to move somewhere where we would be reasonably sure that we would be comfortable keeping it there for several years, because we really don't want to be having the conference where we introduce new people and we have relatively few return attendees to also be the conference where we're in a new location every year.
I guess on that point, so obviously, as you say, there's an advantage to being at a permanent location for then being a destination where new people can come in. But that also presumably has a bias towards people near that location. How do you think that balance shakes out? Obviously DNA has a very different approach where it is in a different place pretty much every year and kind of oscillates between North America and outside North America.
I mean, to be honest, I would say the way FNANO and DNAX work, I would argue is almost an inevitable evolutionary conclusion of the balance you described, in that if FNANO had not stayed in the same place, I think DNA would have stayed in the same place every year. You know what I mean? I think there's a reason we have one conference that moves and one conference that stays put. And then also we have, DNAX is much larger than FNANO. Many more people go to that. And that's in many ways intentional because FNANO is designed around having only one track at a time. Is it good? Is it bad? I think it exists within the ecosystem of the field as a whole. And that's part of why it's a very interesting and complex problem, because you can't just change the whole ecosystem. Not quickly. That would be a crazy thing to do. But you also can't stay perfectly the same. And so it will be interesting to see what happens And what I'm hoping to do, I need to bug the folks doing DNA this year, is I found getting the feedback from Google Forms this year to be quite helpful. Mostly it told us what we already knew, but what I would like to start doing is get more of that information from both DNAX and FNANO and to be able to compare the two. Because one of the things, and I'd have to bring up the forms, very few people who are at FNANO also go to DNAX. I would guess that the folks who go to DNAX have been to an FNANO. And so if that is the case, how does that information inform the way that we as a community make these conferences roll? And because I don't have all that information, I can't really answer the question.
For people who have only been to one conference or the other, what do you think they might be missing out on?
Well, I've only been to FNANO. I have never been to DNAX. I think that's actually one of the things that I think is really valuable about the Molecular Programming Society, is that it very much bridges the FNANO DNAX communities. And that's actually the thing I would say is the most important that I want to focus on in contributing as co-organizing, is to provide a better understanding of what the ecosystem is. I'm not sure it makes sense to change anything until you know what the ecosystem is. And I think it's a lot of work to understand that. And I suspect I will put in a ton of work to understand that, and then some poor sod after me is going to come in and use that information. I would guess that the DNAX FNANO divide probably falls pretty heavily along the circuits and computational side of the field and the structural side of the field.
I think it absolutely does.
And I would guess that part of bridging that gap is going to be that killer application space where we're finding things where you need a structure to interface with some other system, whether that's signal amplification for a biosensor or whether that's doing something in a cell. And in order to do the thing and make it useful, you also need some kind of computation based on DNA, some kind of stimulus response that can be programmed and be made nuanced. And that will drive more melding between the communities, and that also melding between the communities will encourage that type of very profitable research. So if I were to wildly speculate about the future of the field, again, wild, imagine like me dancing around while I'm saying it, would be that we'll probably see, there are a whole bunch of societies that will do kind of on-demand special international conferences. So I wouldn't be shocked if someone made a Gordon Research Conference that was a one-time topic on this, or made something through American Chemical Society or Materials Research or Biophysical. And if that one-time international conference built around the blending between those parts of our communities was successful, I think then those involved in DNAX and those involved in FNANO would see that and go, okay, how do we tweak each of these conferences to meet this larger need? Because I don't think the field is big enough to have 3 recurring conferences. And so, although we might be getting there, I actually don't have anyone with estimates of how big the field is properly. That's something I actually started a metadata project for at NIST, and then we lost our research librarian. But I would guess that we're not quite big enough for a 3rd conference. So I think the catalyst will be some folks organizing a one-time, something or other through an outside society, and that's going to then springboard into, who knows.
Just to throw it out there is the Gordon Research Conference on RNA nanotechnology, which doesn't have a ton of overlap, but you see some of the same people.
Yeah, and I went to the Gordon Research on self-assembly this year, and it was all chemists.
Yeah, that one I looked into, and I just had no talks of anybody I knew. So
yeah, I was there. Some folks from Hanadi Sleeman. I think there were some folks from her lab, and there were a few other people that I recognized from other places. So there were 4 or 5 people at that conference that were DNA. I would guess it would have to be a new thing organized, because it would be pretty difficult to herd cats to convince a sizable portion of the DNA people to all show up at some new conference and be like, hey guys, we're taking over your conference now, wacha. Sound effect clearly necessary for that.
definitely.
I think what will be interesting is coming back to some of these conversations in a year or two, because I think the Molecular Programming Society, since all of us here are involved in it, we all want it to succeed, but I think it is yet to succeed at its goal. When it succeeds at its goal, if it succeeds at its goal, it better. Then there's the question of what does it do next? And that's been a discussion with the executive board. I'm not sure if that's something that's come up in this podcast, but the general thought being there will be something next after the Art of Molecular Programming textbook. And I think once that textbook is out, there will be interesting discussions within our community because some of these questions about DNAX and FNANO will have started to resolve a bit. And I hope we will have a better idea of what our community needs in order to take this technology from something that's nascent to something that is being used in real products and that matters to the world economy.
Well, what a note to end on. Thank you so much for joining us, Jacob. Stay tuned to our newsletter or Slack for details on our next podcast episodes, and thanks for listening.